Hi, everybody. It's Professor Mitchell. We're finishing up Chapter 2 today. Woohoo! Polynomial and rational functions. And this is Section 2.7, Polynomial and rational inequalities. So only a few objectives in this section. We're going to solve polynomial inequalities, solve rational inequalities, and then solve problems modeled by polynomial or rational inequalities. So a polynomial inequality is any inequality that can be put into one of these forms. F of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0, where f is a polynomial function. So I like to talk for a minute about why we solve these inequalities the way we do. So remember that polynomial functions have graphs that are smooth and continuous, which means they can't skip points. The only way they can switch from being positive to negative or negative to positive is by crossing the x-axis. So the first step in figuring out where a polynomial is positive or negative is to figure out where it crosses the x-axis. Now, when I say crosses, I really mean touches. So it could cross right through like you see here, or it could just touch the x-axis and then turn around and go back the other way. All right. So the first step, again, in solving these inequalities is knowing where the polynomial function has x-intercepts, really. Okay, so here's a list of steps for how to solve a polynomial inequality. So the first step is to express the inequality in the form f of x is less than 0 or f of x is greater than 0. And by the way, that does include less than or equal or greater than or equal. So the point is to get 0 on one side. And then solve the equation f of x equals 0. The real solutions of that equation are the boundary points. Remember, we talked a few sections back about how the solution to a polynomial equation like this gives you the x-intercepts. Then what we're going to do is we're going to plot these boundary points on a number line, which will divide the number line into intervals. And then we will choose one representative number called a test value within each interval and evaluate f at that number. If the value of f is positive, then f of x is going to be greater than 0 for all numbers in that interval. Because remember, it can't change sign anywhere except at those boundary points. All right, so if it's positive for one number inside the interval, it's positive for all numbers inside the interval. And similarly, if the value of f is negative, then f of x is less than 0 for all numbers in the interval. So lastly, you write the solution set, selecting the interval or intervals that satisfy the given inequality. If there's more than one interval, you join them together with union signs. This procedure is valid if less than is replaced by less than or equal, or greater than is replaced by greater than or equal. The only difference is that if your inequality involves less than or equal or greater than or equal, you're going to include the boundary points in the solution set, because those numbers will make f of x equal to 0, which will automatically mean that it's less than or equal to 0 or greater than or equal to 0. Hopefully that makes sense. All right, so here's an example. We're going to solve and graph the solution set of the inequality x squared minus x is greater than 20. So the first step is to write that inequality in, I guess we could call it standard form, with 0 on one side. So we're going to subtract 20 on both sides, and that's going to give us x squared minus x minus 20 is greater than 0. So we've already done that part. Now we're going to solve the equation f of x equals 0. If x squared minus x minus 20 equals 0, remember you solve an equation like this by factoring, if you can. This polynomial factors into x minus 5 times x plus 4. So of course, the only time x minus 5 times x plus 4 could equal 0 is if x is 5 or x is negative 4. So those are going to be our boundary points. All right, so here are the boundary points plotted on a number line. These boundary points separate the number line into 3 intervals. All right, there are the 3 intervals. So what we're going to do next is we're going to pick a test value within each one of those intervals. So we'll start with the interval negative infinity to negative 4. And we're choosing the test value negative 5. You could pick anything that's less than negative 4. Substitute that value into the function f of x equals x squared minus x minus 20. It comes out to 10, which is positive, which means that this function is positive for all x's in that interval. Okay. Moving on to the next interval, which was negative 4 to 5. I always pick 0 for any interval that includes 0. When you put 0 into that function, you get negative 20, which of course is negative. And that means the function is less than 0 for all values in that interval. And finally, the interval from 5 to infinity, the test value is 6. If you substitute 6 into this function, you get 10, which is positive, and that means this function is positive for all x in the interval 5 to infinity. So what does all that mean? Well, we transformed the original inequality into one of the form f of x is greater than 0. So there were 2 intervals that satisfied the inequality f of x is greater than 0. Those intervals were negative infinity to negative 4 and 5 to infinity, which means the solution set of this inequality is the set negative infinity to negative 4 union 5 to infinity, which you can see on this graph right here. It's a little hard to see the part that's colored in blue and also the part that's colored in red. Okay. So I will admit these problems do have a lot of steps to them, but I think the steps are logical. So, you know, the secret is just like with a lot of other things, it's just practice, practice, practice. All right, moving on to rational inequalities. A rational inequality is any inequality that can be put into one of these forms where f is a rational function. So remember, we just talked about rational functions in the last section. A rational function is the quotient of 2 polynomials. Okay, so again, I wanted you to kind of understand why this works the way it works. So solving a rational inequality, it's the same idea as solving a polynomial inequality, except that the graph of a rational function can jump over points, right? And that happens whenever the function is undefined. So that will normally happen whenever you have a vertical asymptote, okay? So it just means that in addition to the x-intercepts, we are also going to have to include values of x that make the function undefined as boundary points. All right, now I wasn't crazy about the way the PowerPoint from the publisher explained this, so I decided to bring in something of my own, sort of. All right, so these are the steps that I like to follow when I'm solving rational inequalities. Again, it's very, very similar to what you saw for solving polynomial inequalities. Just notice there is a new step 1. So the first step is to solve for values that make all denominators 0. So any number that makes a denominator 0 is automatically a boundary point. Now, I say this a little differently than your textbook does. What I like to do for step 2 is just solve the related equation. They talk about getting 0 on one side, and that's okay. I happen to think that's a little bit more work than doing it my way, but we'll do it that way. It's fine. All right, so at this point, you have a bunch of boundary points. You have the values that make any denominator 0, and you also have the solutions to the related equation. So we're going to take all those boundary points and plot them on a number line. From this point on, it's basically the same as what we did with polynomial inequalities. And then for each interval that is created by those boundary points, you choose a test point, determine whether its value satisfies the original inequality. All right, and then there is one little thing that's different in the last step. The solution set includes the regions whose test point value is a solution. Check whether to include values from step 2. Now, what I mean by that is if your inequality symbol is less than or greater than, the values from step 2 are not included. But if your inequality symbol is less than or equal, greater than or equal, then they are included. However, the values you found in step 1, the ones that made a denominator 0, those ones are never ever included. Okay. All right, so we have this example, and I'm happy that it is a greater than or equal. We're going to solve and graph the solution set of 2x over x plus 1 is greater than or equal to 1. Okay, so they're going to follow, their list of steps is a little different from my list of steps, but it gives you the same thing. So they're saying to express the inequality so that one side is 0 and the other side is a single quotient. So that looks like this. Right? This part crazy about this is more work than the way I do it, but it's good practice. So first thing we're going to do is subtract 1 from both sides. That gets us from here to here. Now, in order to get this thing to be a single quotient, we need to have a common denominator. That common denominator would be x plus 1. So we're going to multiply 1 by x plus 1 over x plus 1. Okay. Now we have our common denominator, so we can combine those two into a single fraction. Distribute the minus sign so that we can simplify this expression on top. And that gives you x minus 1 over x plus 1 is greater than or equal to 0. That inequality is equivalent to the one that we were given. Okay, so next thing we're going to do is set the numerator and the denominator of f equal to 0. So just comparing their steps to my steps, the denominator is going to tell you where the expression is undefined. So that's what I was describing in my step 1. The values of x that make the numerator 0 are going to be the values for my step 2. Okay. So, of course, if x minus 1 is 0, that means x is 1. And if x plus 1 is 0, that means x is negative 1. So these are our boundary points. We're going to plot them on a number line. And now that creates 3 intervals. So just like before, we're going to pick a value inside each of those intervals and put it into the new inequality. Right? The one advantage that I can say for their method is that if you put it in the form f of x is greater than or equal to 0, then you just have to look at whether f of x is positive or negative. You don't have to look at the actual value of f of x. I think they end up looking at it anyway, but all right. Okay, so these boundary points create these 3 intervals. All right, so going with the first interval, our test value is negative 2. If we put negative 2 into this function f of x equals x minus 1 over x plus 1, it comes out to 3, which of course is positive. And that means for all x in that interval, f of x is greater than 0. Next, we have the interval from -1 to 1. Of course, they chose 0 for their test value. You put 0 into f of x, and you get -1, which is negative. Oh dear, there's a typo here. I did find some typos before I started this. Did not see this one. Okay. I bet you this is just a sloppy cut and paste. They just forgot to change this. Okay. You see why that is, right? F of 0 equals -1, which means the function is negative, less than 0, for all x in that interval. And finally, we have this interval. The test value is 2. If you substitute 2 into this function, you get f of 2 equals 1/3, which is positive. The conclusion is f of x is greater than 0. That is correct this time, for all x in the interval from 1 to infinity. All right, so step 5, write the solution set, selecting the interval or intervals that satisfy the given inequality. The solution set of the given inequality is the union of the intervals -infinity to 1 and 1 to infinity, where the 1 is included, but there's another typo. Sorry about that. Okay, the 1 is included, but the -1 is not. So let's talk about this for a second. The reason the -1 is not included is because that's the value that made the denominator 0. So that cannot be included, all right? The 1 made the function equal 0. And the new form of the inequality was f of x is greater than or equal to 0. Since the number 1 makes that function equal 0, it is included as a value for this solution set. Okay. All right, and the graph of this solution set would look like this. So you have, let's see, what is that? Looks like everything is green this time. Up to -1, not including -1. And then from 1 to infinity, including the 1. All right. Again, I know it's, you know, quite a bit of steps. Practice, practice, practice. Actually, I think you might have a chance to practice right now. So we're going to do this application. An object that is falling or vertically projected into the air has its height above the ground, s of t, in feet, given by this formula, s of t equals -16t squared plus v0 times t plus s0. So if you've taken physics, you've probably seen this formula before. V0 is the original velocity or initial velocity of the object in feet per second. T is the time that the object is in motion in seconds. And S sub 0 is the original height of the object in feet. So in this specific example, an object is propelled straight up from ground level with an initial velocity of 80 feet per second. So its height, please ignore this extra apostrophe, that should not be there, at time t is modeled by s of t equals -16t squared plus 80t. So that fits the formula that we had on the previous slide, right? V0 is 80 and s sub 0 is 0 because we're throwing the object up from the ground. So s sub 0 is 0. All right, so the question is, in which time interval will the object be more than 64 feet above the ground? Okay. So once we set up this inequality, I'm going to ask you to pause the video and try to solve that polynomial inequality. And the inequality looks like this thing really has a lot of typos. I am so sorry. I don't know where they got 18. Da, 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 da. Let's do it like this. Okay. All right, so the height of the object is given by S of t. I'm trying to make this an 80. It's not working out very well, so maybe I'll just put the 80 here like this. Okay. So the inequality that we need to solve is negative 16t squared plus 80t is greater than 64. So at this point, if you would like to pause the video and try this one, I think it would be really good practice. And then come back and we'll compare notes. All right, let's see. So the inequality is in the form f of t is greater than 0. Well, it's in that form once we get to this step anyway. All right, we have negative 16t squared plus 80t is greater than 64. If we subtract 64 from both sides, we get negative 16t squared plus 80t minus 64 is greater than 0. So we will continue solving this inequality by solving the equation to find the boundary values. So if negative 16t squared plus 80t minus 64 equals 0, let's factor negative 16 out of that polynomial. That's going to leave us with negative 16 times t squared minus 5t plus 4 equals 0. T squared minus 5t plus 4 factors into t minus 1 times t minus 4. So the only way that the product of these three things could equal 0 is if either t minus 1 is 0, which means t is 1, or t minus 4 is 0, which means t is 4. So our boundary values are 1 and 4. So let's set up our number line. Here's the 1, there's the 4. Notice they're starting this number line at 0. Because this is an application problem, it doesn't make any sense for t to be negative. All right, so we'll just consider values of t that are greater than 0. All right, so starting with, oh, okay, so they left out a lot of their work here. You know what? Would it be a good idea to switch over to the tablet? I wasn't planning to do this, but it might be a good idea. Give me just a second to get that going. All right, let's get rid of this from last time. All right, switch over to the tablet. Here we go. Whoops, stylus. There we go. All right, so the function is f of t equals negative 16t squared plus 80t minus 64. All right, so I'm going to do it like this. I'm just going to put it all in one chart. You've got your interval. Here we'll put our test value. I can't remember how they labeled this next part, but I'll label it inequality, and then a conclusion. By the way, my handwriting is much nicer than this in real life. It's hard to write on the tablet, for me anyway. Okay, so the first interval was from 0 to 1. So unfortunately, we're going to have to use a something that's not a whole number for our test value. We'll go with 0.5 or 1/2. Okay, this is going to be kind of a mess. I don't know if I'm actually going to get this all on one slide here. Okay, so negative 16 times, let me switch to a thinner pen here. 1/2 squared plus 80 times 1/2 minus 64. Okay, let's do some quick math here. 1/2 squared is 1/4. 1/4 times negative 16 is negative 4. 80 times 1/2 is 40 minus 64. Well, that's definitely going to be negative. It's going to be negative 28. Okay, which is negative. So in that interval, f of t is less than 0. All right, I am going to try, I'll try squeezing this in the last two. I'll be able to use whole numbers as my test values for these other two intervals, so maybe it'll work. Next interval was from 1 to 4. I will use 2 as my test value. So really what we're looking at here is the value of f of t. All right, so negative 16 times 2 squared plus 80 times 2. I think this will work. Minus 64. 2 squared is 4. 4 times negative 16 is negative 64. Negative 64 plus 160 is 96. 96 minus 64 is 32, right? And that's positive. So in that interval, f of t is greater than 0. And then finally, the interval from 4 to infinity. Shall we go with 5 for our test value? Negative 16 times 5 squared plus 80 times 5 minus 64. 5 squared is 25. 25 times negative 16 is negative 400. Negative 400 plus 400 is 0. 0 minus 64 is negative 64, which is negative. So in that interval, f of t is negative. All right, and I believe the question was, when is f of t greater than 0? Because that's equivalent to asking when is the original position function greater than 64? So we are interested in this interval right here. And if we go back to the slide, I think that might make a little more sense now. When we test the intervals 0, 1, 1, 4, and 4 to infinity, we find that the inequality is true for the interval from 1 to 4, which means the object will be more than 64 feet above the ground between 1 and 4 seconds, excluding t equals 1 and t equals 4, because at those times, the object is exactly 64 feet above the ground. So they don't make it into the solution set, just barely. That's going to do it for section 2.7, and that's going to do it for us for chapter 2. So we'll see you next time for chapter 3.